Buenas tardes a todos. Creo que podemos ir comenzando, por respeto a los que están puntuales hoy. Mi nombre es María Florencia Segovia y en nombre del del capítulo profesional Colombia, SPWLA Colombia, para mí es un placer y un honor darles las bienvenidas a todos en este que es nuestro segundo webinar del año, con un tema tan interesante como lo es el Reservoir Geodynamics y con un ponente tan destacado como el señor Oliver Mullins. Así que, bueno, muchísimas gracias por sumarse, por su tiempo. Bueno, aprovecho entonces este espacio antes de comenzar con el webinar para invitarlos a que se sumen a la SPWLA Profesional Capítulo Colombia. Realmente son muchos los beneficios, principalmente la red de contactos, el acceso a estos eventos técnicos, a entrenamientos también, a cursos que estamos planeando y organizando para este año, con algunos beneficios, sobre todo para aquellos que sean miembros activos del capítulo. Y también invitarlos a que se sumen, a que participen de eventos que realizamos presenciales, tanto el año pasado como pretendemos hacer también este año, en modalidad workshop. Y como les mencioné, vamos a tener beneficios para aquellos que sean miembros. Entonces, ¿cómo se pueden afiliar? ¿Cómo pueden asociarse? Bueno, para las personas o aquellos profesionales que estén radicados en Latinoamérica y pertenezcan al grupo 2, hay una fee especial de $40 anual. Para estudiantes también este año ha habido una reducción del fee y actualmente es de $6. Y también hay una forma de afiliarse sin costo que tiene un acceso más limitado a los recursos o a los beneficios que tiene la SPWLA Internacional, pero que también les permite visualizar y seguir las actividades que se van organizando, que va organizando la SPWLA, los distintos capítulos. Entonces, bueno, los invitamos a que nos sigan en redes, a que, bueno, nos pueden seguir en Instagram, nos pueden escribir por Gmail, también nos pueden seguir en LinkedIn o nos pueden enviar un correo al correo oficial, valga la redundancia, del capítulo Colombia. Y bueno, para cualquier duda, cualquier inquietud, o si bien tienen intenciones de sumarse al comité o bien como afiliados. Entonces, bueno, para no quitarle más tiempo al ponente, Ulises tiene la palabra.
Muchas gracias. ¿Me escuchan? Yep.
Sí, Ulises.
Okay, muchas gracias. Welcome everybody. Especially welcome to Dr. Oliver Mullins for joining today. Oliver is a Schlumberger Fellow and member, U.S. National Academy of Engineering. He is currently leading the new discipline named Reservoir Fluid Geodynamics. This is a new discipline, and we are going to learn about this today. Dr. Oliver, he wrote 2 books, co-edited 3 books, co-authored 300 publications, and co-invented 141 US patents. He has received 7 international awards from 4 organizations, ACS, SPE, SPWLA, and ADIPEC, including the Anthony Lucas Gold Medal from the SPE and the George Ola Award in hydrocarbon or petroleum chemistry, and a 2022 pioneer in energy research, both from the American Chemical Society. That being said, we welcome Oliver. So Oliver, thanks again, and everything is yours now.
Thank you, Ulysses, and thank you for this opportunity. Let's see, so I'm sharing my screen, I think, and now you can see. So first I have to apologize. This presentation is in English, not Spanish. My wife is Venezuelan. You might think I would know how to speak Spanish, but I claim I have a horrible professor. She says she has a horrible student, and I'm afraid we're both correct. So that's too bad. But anyway, so reservoir fluid geodynamics and reservoir evaluation. So this is the topic of today, and you can get a free copy of the PDF at this link. And that's the last time you'll hear free and Schlumberger in the same sentence. So the outline of today's talk, I'm going to.
Sorry, we don't see your slides.
You don't see the
yet.
Slides?
Not yet.
Let me try that again. So
Yes, please.
it should be share. Sorry, I didn't. Let's try that again.
There you go. Now,
And
now
then,
we can see your screen.
Now you can see, right?
Yeah, we can see the slide number 2.
I just need to get in let me
Presentation
just
mode.
get this presentation mode. Yeah, so the outline, I'll introduce the topic and description, enablers, and methods. I won't spend too long on this, and then we'll look at case studies, which are a lot of fun. And what I have in here, connectivity, fault block migration, gas charge into oil, tar mats, baffling if we get through all this. We'll see. And we're doing simulations. And so what I'll be showing is simulations. Let's see, how do I get rid of this? Do you see this bar across my, oh, just move it. So, we'll look at some simulations. This is a latest thing we're doing, is to test the geologic model with reservoir simulation of the charge history. So we'll look at that. Okay. So what is RFG? And that is shown in this slide. What we're doing on the fluids is copying the workflow that's done on rocks in every reservoir. So in rocks, you always consider the depositional setting, turbidites, deltas, what have you, dunes. And you always consider what happens post-deposition, fault formation, and a lot of locations in the world. I'm trying to get rid of this bar so I don't see, anyway. Salt halokinesis, anticline formation, karst formation. In the oil world, petroleum system modeling fills the reservoir, and that's the analog of deposition of rock. But petroleum system modeling does not handle the evolution of reservoir fluids from the time of charge to present day. There was no name for the discipline. I had to name it. So we named it Reservoir Fluid Geodynamics, and that accounts for oil compositional redistribution in the reservoir during and post-charge to present day. And there may also be phase changes as well in this process. And we have this book about the topic, and that's why if you don't have a book, you don't have a discipline. So I'm claiming this is a new discipline, and we have the first book on the topic. The crucial issue, we had to be able to identify whether the reservoir fluids are equilibrated in today, as you look at present day, or are they continuing to evolve? Another way to look at this is that you could consider the reservoir fluids like a movie, and you get one time frame of that movie. And the question is the time frame that you're looking at in present day the end of the movie, or the middle of the movie, or the start of the movie? To figure that out, you must be able to identify what is the equilibrium state of the reservoir fluids. So we developed the asphaltene thermodynamics. I'll discuss that a little bit more on the next slide. And that was key for addressing this issue. Next, we have the proper scientific foundations, including all the fluid mechanics. We have to measure the fluid gradients. That is what we use to evaluate the thermodynamic theory. We must know the compositional gradients in the reservoir. And then we have to, so we have the theory, the measurement. We have to listen to Mother Nature. What does she do when she mixes these reservoir fluids? And we've done to date about 80 reservoirs in this process. Okay, just a little bit on the thermodynamics. The issue here is that if you ask any reservoir engineer on planet Earth, what's the thermodynamics of crude oil, they'll tell you it's the cubic. That's what's in the simulators. The cubic equation of state is a variant of the van der Waals equation of state, which is itself a variant of the ideal gas law. It's for gas and liquids. It is not for solids. The cubic does not work to launch this discipline. If it did work, then this discipline would have been launched not long after Peng and Robinson introduced the cubic that worked well for handling crude oil. The problem with the cubic and looking at gas-liquid equilibria to determine whether the reservoir fluids are equilibrated is that the error bars on GOR are too big, the gradients tend to be too small, and there are too many parameters in the cubic, you can fit anything. So you can't tell the physics, is the system equilibrated or not? We had to develop the asphaltene thermodynamics for this purpose. And there was a trick involved. We had to solve the particle size of asphaltenes in oil. This took a long time. It took 25 years of my time. And it was a tricky problem. I'll show in the next view graph. But once we resolved that problem, then we knew the size. We could resolve Newton's second law of motion, F equals mg, in a gravity field. And so that became the foundation for the gravity term in the modified polymer solution theory that we used. So that was how we did this. The polymer solution theory we're using is Flory-Huggins theory. Even though it looks like there are a lot of parameters, there's actually only one chemical interaction parameter for the asphaltenes and one for the solvent, the oil, and the one for the solvent, for the asphaltenes is fixed. So we have very few adjustable parameters. Okay, so that makes this a good system to use, and we can measure the concentration gradient of asphaltenes with the optical measurements we have on board the downhole tools. Okay, so the trick is that the asphaltenes have 3 aggregation thresholds, not 1. So at very low concentration, they're present as a true molecular solution in crude oil. As you increase the asphaltene concentration, they form nano aggregates of about 2 nanometers in size with 6 molecules. Higher concentrations, again, you get clusters of 8 nano aggregates or so, 8 of these. And higher concentrations, again, you get bulk phase instability. So this is the light oil model, the black oil model, and the heavy oil model of asphaltene. So that was a trick that made this a hard problem to solve, but we eventually solved it. So the mode of operation, we just measure the fluid gradients with the downhole formation testing tools. And then we plot the gradient data, just asphaltene content on TVD. And of course, we're measuring GOR and everything else too. So we were plotting everything. But the foundational question, are the reservoir fluids equilibrated? If the answer is, if the data fits the Flory-Huggins equation of state, then it appears that the fluids are equilibrated. We need still more measurements to validate that. Okay, this is a thermodynamic approach, which thermodynamics is looking at dissolved gas, liquid, and dissolved solid and treating gradients of that. We link this with petroleum geochemistry. I presented to 10 geochemists earlier today. And for our purposes, we like to use 2D-GC. And actually, this example came out of the Llanos Basin in Colombia. And what you see here is 2D-GC with all of the N-alkanes. So we have 2 columns. We get two axes of separation. It's much like you have an NMR when you go to two-dimensional NMR. Where you're measuring 2 different parameters. Everything separates in an aerial map And this is the same analog of two-dimensional NMR, but this is two-dimensional gas chromatography, separating out all these kind of components from the saturates, the aromatics, the biomarkers, et cetera. Here we're seeing all the N-alkanes, no biodegradation. Here we're seeing that all of the hopanes, or 25 nor hopanes, severe biodegradation. So how can you have no biodegradation and severe biodegradation in the same oil? That's because in the Llanos Basin, the first charge came into this reservoir prior to the subsidence that heated up and killed the bugs. So the bugs ate everything and generated 25 norhopanes. The reservoir continued to subside, heat up, killed the bugs. Second charge came in with all the N-alkanes. So this clearly shows that there's two charges that had very different evolution in time. Okay. So, all right, next, what I want to show is an example. Actually, this one's on the cover of my book. The evolution of this reservoir is shown on the cover of my book. So they're in this, right now, initially they had two wells. Each well had an upper sand and a lower sand. The question was, what's the lateral connectivity across the reservoir in the upper sand, and what's likewise in the lower sand? And in addition, what's the vertical connectivity between the upper and lower sands? This Deepwater Gulf of Mexico with Talos. So what we're showing is the asphaltene gradient data plotted up, matching the FHC EOS in each of the sands. The lower sand, the pink curve, is matching the FHZ. The upper sand, the green curve, is matching the FHZ. So laterally, each sand is connected. And that is in agreement with the seismic imaging, which is showing the thickness, the isopac maps of the upper horizon and the upper reservoir, the lower reservoir, and the intervening hemipelagic shale break in between. And there's the shale, as you can see. The seismic, however, was showing a big pinch out, but the problem is seismic resolution is many meters, so it's not clear that that's an actual pinch out. The asphaltene gradient data is saying that the upper and lower sands are not well connected. They're offset from each other. You need accurate data to be able to make that assessment, but we have the accurate measurements. So we told the operator the upper sand is not well connected to the lower sand. This was a CEO, a presidential well, went right to, I met with a CEO on this. They started producing in this T1 sidetrack, and after production started, they drilled this T2 sidetrack and checked what the depletion pressure looked like in the pinch out area. And what you can see in the pinch out area is a depletion pressure offset between the upper and lower sands. It means that they're not well connected in the pinch out. The seismic pinch out is showing, well, in wireline, 4 feet of shale, which is plenty to act as a substantial baffle between the upper and lower sands, but it's invisible in seismic. It's only 4 feet. So the evaluation of the DFA data was correct, and the seismic was optimistic in assessing reservoir connectivity vertically. Okay, then they had this T2 sidetrack in the down-thrown block. And here's the asphaltene gradient data lining up, matching the central, that's the down-thrown block. So what we're going to do is reconstruct the reservoir on the next slide. So we reconstruct the reservoir, and what you can see is the asphaltene gradient data, when lifted up by the fault throw, interpolates into the asphaltene gradient data in the central fairway. So what that means, we had anticline formation, oil charge, asphaltenes equilibrate on these curves, and then the fault through. So that's quite a sequence of events. This is only a Middle Pliocene reservoir, so it's been busy, 3 million years old rock. What you can also see here is that the isotopes, methane isotope, carbon isotope of the down-thrown block differs and is heavier than the methane isotope in the central fairway. The isotope ratios of methane, the C12 to C13, tell you whether or not you have biogenic gas that has entered the reservoir. in this, so the thermogenic gas is about -40 per mil, biogenic gas about -70. So being -60 in the central fairway says that 2/3 of the gas in the central fairway of the methane is from a biogenic source. In addition, the heavier carbon in the downthrown block says that there was less biogenic gas charge into the downthrown block than into the central fairway. This means that the gas charged after fault throw. So you have a sequence of events, or essentially the geoscenario of the reservoir. Now, the other remarkable thing here, if you look at this, the isotope ratio of the entire central fairway, both upper and lower sands, is the same. We had excellent mixing of the gas charge with the oil. The question is, how did that happen? So now I have to look at mass transport in reservoirs over geologic time. You can ask, can diffusion account for the mixing of the gas and oil? So in other words, if I had a gas charge first and then an oil charge, well, could I diffuse the gas into oil in my 2-million-year-old reservoir? The answer is no way. The expected distance of some component loading from diffusion, starting at the surface and diffusing in 1 million years, you're only going about 80 meters or so for significant compositional loading from this diffusional process. It would take even 10 million years will not get you a value of a invariance ratio that we see. Even 10 million years, it would have to be 100 or maybe many hundreds of millions of years. So either the oil got there before the rock, or it's not a diffusional process. So you can ask natural convection by thermal gradients. There's no way that will cause gas to convect down. There's no way. It's just too big a density contrast. It's not associated with colloidal instability. We can show that, but I won't go into detail on that. The only way to mix the gas and oil is forced convection. What forced convection is when you have a pump or Mother Nature adding a low density fluid at the base of a column of high density fluid. That will force convection. That's in that process. And that's what we had to have. Now this, you then ask, well, the biogenic gas is produced at cold temperatures, the thermogenic gas at high temperature. So how can you add this cold temperature gas that's created cold temperature to a hot reservoir? And the answer is gas chimneys. You can fill reservoirs shallow with gas, bury them, break the reservoir, and then gas is seen in seismic throughout, going from various traps to surface. And they can go through the Cretaceous or what have you. They can easily charge into reservoirs. So gas chimneys are a mechanism to deliver gas that was formed shallow, deliver that gas to Cretaceous reservoirs or whatever depth. So, okay. So then we think we have this process taking place in our reservoir that gave rise to that huge mixing. Let's take a look at what happens in simulation. So what we're simulating here is a reservoir, 3,000 feet in width, 1,000 feet of oil column. This is water, and we're adding gas at a point charge and asking how well does that gas mix. And so what you can see, the color code is the GOR of the oil that's produced. So after we've added 44% of the total gas volume of this reservoir, again, this Talos reservoir with the downthrown block and the central fairway, after we've added 44% of the gas, you can see the streamlines are reaching out across the entire reservoir, pulling the low GOR oil from the eastern flank over here to the western flank in this image, and bringing that low GOR oil to the point of gas charge. And what you generate in this mixing process is a single GOR across the entire reservoir. So that's what's happening here. This is several time steps of this gas charging process, and in each time step you have a single GOR across the whole reservoir. And that means that you have excellent mixing of the methane that came in as a separate gas phase. But in these high pressure reservoirs, the methane dissolves in the Gulf of Mexico's high pressure province. The gas dissolves into the oil and it convects up as the gas makes the oil lower density. It convects up in its forced convection process and stirs the entire reservoir. And that accounts for how the central fairway gas fraction was the same fraction of biogenic to thermogenic methane throughout. You may recall, though, that I had an upper sand and a lower sand. So here we're going to simulate that. We're going to add the methane again at the oil-water contact, and look what happens. So here's a little bit of gas added, 20%. And what we're doing is we're adding the gas below the shale baffle with a hole in it. And once we add gas to the oil, it becomes lower density, and the oil above the shale break just drains through the hole like oil out of an oil pan in a car. And as we keep adding gas down below, we've expanded the volume of the fluids. And as we keep adding gas, the heavier oil from above drains through the hole, and you get superb mixing above and below the shale baffle, even though the hole is rather small. So this accounts for why it is that we saw this single isotope ratio, single fraction of added biogenic gas to the thermogenic methane in solution. Okay. Now I'm going to address another reservoir that's famous, the Hani bottles from Hani El Shahawi, who was in Shell for a long time, Schlumberger prior to that. This is a single deep water reservoir with a gigantic gradient, which you can see with your eyeballs. So it's a single tilted sheet reservoir against salt. There's a variation of the isotope ratio. We're going to look at that. So here's all the data downhole in lab from this reservoir. So first I want to look at the GOR. The GOR in the top half of the reservoir goes from 8,000 scuffs per barrel to 2,000 scuffs per barrel in only 40 meters. It's a gigantic disequilibrium gradient. The bottom half of the column is matching the cubic EOS, which is the dashed line. So the bottom half of the column looks like it's equilibrated, but the top half is far from equilibrium. And what we're showing is that we can match the top half of the column to the fixed second law, the solution, error function solution to fixed second law. So in other words, this is a diffusive gradient of methane diffusing into the column from the top, but it's only gotten about halfway down the reservoir. It hasn't gotten to the bottom. And so that's why everything at the GOR at the bottom is unperturbed by this diffusing gas. The increase of solution gas expelled the asphaltenes. They migrated to the base of the reservoir, and they're matching the heavy oil model, even though the asphaltene content is not so high. But all that added gas destabilized the asphaltenes into the clusters, thus the heavy oil model. If you look at the isotopes, you can see the diffusive gradient of the gas diffusing into the oil column. But the puzzle has been that the gas at the base of the column is 50% biogenic gas, 50% thermogenic gas. That biogas did not get there by diffusion. The loading is almost zero by the time you get halfway down the column. So the question is, how do you create such a column where you have a diffusive gradient up top, what looks to be equilibrated gradients at the bottom, and 50% of the gas at the bottom is from biosource? How did that happen? Well, here's the process. We can now model it even. There's the modeling and the cartoon results to match the model. First, we had an oil charge. Then we had gas come into the oil. And as we saw previously, the gas comes in and mixes across the entire reservoir, causing a single GOR in the reservoir at the time of charge. But we added so much gas to this reservoir that the oil became saturated with gas. It can hold no more gas. Then the excess gas that's added after we saturate the oil with gas, all the extra gas goes up to the top and forms a gas cap. At which point gas entry stops, but we have a subsidence process continuing in the Gulf. So we're subsiding the reservoir, the pressure goes up, and now the oil becomes undersaturated and gas can diffuse into the oil column. So these are the processes that account for the handy bottles, which this shell reservoir was in the literature for 15 years unexplained. We finally explain it and model it. And I guess I'll do one more reservoir. Well, we'll see. This is a couple of reservoirs, well, 3, but I'm going to only show 2, fault blocks 1 and 2 from Norway offshore. So here we see a reservoir with a disequilibrium gradient of GOR, a disequilibrium gradient of asphaltene. So it's looking somewhat like the Hanny bottles with gas diffusing into the oil column. Now it's only 40 meters. So how come it's not equilibrated? There are 2 answers to that. Number 1, it's a Pleistocene charge. So it just happened a few weeks before I was born. The second reason is that this reservoir has a lot of shale baffles. Those shale baffles showed up in vertical interference testing in wireline and also showed up in low productivity index in well testing. And that the baffles slow down equilibrium. The diffusing methane has to go around the baffles to get to the base. In this fault block, the asphaltenes are at low concentration and equilibrated, and the GOR is also equilibrated and very high, 200 cubes per cube. When the GOR goes up that high, the asphaltenes are expelled out of the oil. They first migrated down. So this was reservoir description was what this reservoir went through in its geologic past. But the process of gas diffusion down and asphaltene migration down is complete over here. So we have equilibrium of the liquids and the asphaltenes were expelled. This reservoir did not have baffles and was 10 times higher PI than this reservoir. And of course, this is the first target, but they have a tar mat, which is going to interfere with aquifer support. Okay, and we can look at the tar mat in SCM imaging, very high resolution imaging. So we're looking at pores. Here, the core is obtained from where the asphaltene content was about 35%. That is the maximum solvency of asphaltenes in oil, 35%, and it's just starting to precipitate. The asphaltenes are just starting to precipitate on the core. In this case, the higher GOR expelled all the asphaltenes. There's very little asphaltene left in the oil. The ODs are close to 0. And so the asphaltenes are depositing, but they're not space filling because the asphaltenes are depositing out of oil. And as that happens, the asphaltene or the tar is trapping oil that does not have asphaltene anymore. And those traps are nearly spherical. You can see the traps in the tar. Okay, so that's a movie, by the way, that's a movie of tar mat formation. It's only 2 time frames, but it's one more time frame than anybody else. It's still a short movie, but actually it took about 1 million years to grow this tar mat like this. Okay. I guess I'll do this last reservoir and then that'll be it. So this is a fun reservoir. At the top, there's a monotonic gradient of asphaltenes in the sand, but it's not equilibrated. It does not match the use of the Flory-Huggins-Zoo equation of state with our nanostructure model of asphaltenes. That means that this is not equilibrated. And so why not? And so this well I'm showing is at the crest. This is the seismic image of a comparable reservoir. And what they had was overturn, formation overturn. And in fact, this well with the black dots in the crest was where the well came in the bottom of the reservoir, went through nothing but sand in the reservoir, and came out the bottom of the reservoir. This is all sand, but it's not equilibrated. And because the flank is equilibrated, it means this will not produce well, and it had a bad test. Subsequent to our informing the client, this will not produce well, they showed that we were correct, it had a bad test. In one flank, they had a density inversion, high density fluid over lower density fluid, as shown clearly by the asphaltene content. So that's all compartmentalized, will not produce well. And they had lousy production there. They also had some blocks filled with water. So things were not too good there and compartmentalized. In the other flank, there were two wells, the green well and this whatever color that is, pink well, they on dip. And so not too far apart. And the asphaltene gradient data looks equilibrated, matching the black oil model of the FHC. So we told the operator that will produce well, and indeed it did. So the question remains, though, why did a well that went through nothing but sand not produce well, even though it was only about 1,000 feet? Why is that? And the reason is, is deformation banding. So when you take sandstone and distort it and manipulate that sandstone, you can powderize the sandstone. And so what we're seeing in whole core CT scanning is and you can see it also in quantigeo scans, you can see evidence of the deformation bands. And we're seeing the deformation bands show up two separate conjugate sets of deformation bands. So the yellow is one conjugate set, and then the white is the second one. And those deformation bands are associated with powderized, these are cataclastic deformation bands associated with powderized sandstone. And in the deformation band itself, the perm can drop orders of magnitude. And this deformation of the sand, making it from horizontal to vertical, was accompanied by massive distortion of this kind of cataclastic deformation banding in the crest. And that's what gave rise to poor production in this well. Okay, so that's all the reservoirs. I'll just wrap up. And so the idea now is that we're looking at the mixing extent in reservoir fluids. We're addressing this both from thermodynamics as well as all the geochem parameters, both. The mixing is controlled by the time since charge. Sometimes it's 1 million years, sometimes it's 100 million. Reservoir architecture is key. Do we have baffling? Do we have an aspect ratio that's not too big? And we're still looking at the importance of the fluid properties, density, contrast in the fluids, and how that interfaces with these other parameters. Excuse me. So that's it. So we have a new workflow. So we can now test what kind of mixing. Do we have no mixing, total mixing, partial mixing, like the shell example? We have a huge range of potential mixing. So we have a new way to test reservoir architecture by modeling. It can even be in 2D to model a key attribute of the reservoir, like connectivity or baffling or what have you. And so the idea is we can characterize what came into the reservoir within a petroleum system context, but we don't really need to do petroleum system modeling. And we can model the charge of the fluids that came into the reservoir, which depends on key attributes of the geologic model, and compare the predictions of modeling, can even be 2D, like I say, and compare that with all kind of measurements of the thermodynamics as well as the geochem. So we think that this will be a popular way to get into workflows for assets, because every asset, every reservoir is simulated. So we can now use simulations in a new way. The simulations I showed today are all with Eclipse. Okay, so RFG enables the same workflow for fluids, looking at the evolution over geologic time, as always used for rocks. RFG can address all kinds of properties, reservoir architecture and fluid issues and aquifer support, all kinds, even wax. We have several case studies. We have a new workflow, history match reservoir charge. This is a new way to test a geologic model prior to any production using simulation. Compare predictions of the simulation with measurement of the current fluid distributions. And we have done 80 reservoir case studies with operators all over the world. We're very flexible in how to proceed. So that's it. You can get that book, and the PDF is on that website. I showed on slide 1, and I'll just show up that slide. So if there are any questions, I'd be glad to take them, or however you want to do this.
All right, Oliver, thank you so much. It's a great presentation. There is a lot of content to digest.
Yeah, that's a lot.
No, but it's
decades of. I know it's not easy. It's
yeah,
it took a long time to get here from starting.
Yeah, absolutely. Do we have any question on the chat window, or does anybody wants to raise the hands to open the microphone and to ask the question or make any comment on the presentation? Anyone?
That's a bit much, I have to admit.
Yeah. In the meantime, I think I'm gonna open the Q&A session.
Sure.
Oliver, and you can you confirm if the case studies and these studies are done in exploration / appraisal stages, or?
Yeah, that's a good question. They can be done in all phases. So in all kind of reservoirs. So some reservoirs we started with 2 wells, and we're now probably, I can't remember how many now in this reservoir. We started with 2 wells, so we're probably up to, including all the sidetracks, 7 or 8, and they're well into production. In the Middle East, things are a little different. We've done projects where the operator had hundreds of wells, but we don't want to do a reservoir length scale, hundreds of wells case study, because the cost structure, the time structure, it wouldn't be efficient at all. Instead, what we do is, if an operator has many wells in the field and they have questions, could be aquifer support, could be sweep efficiency, whatever the EOR, there are all kinds of questions we've addressed. In those cases, we will take 5 wells or 4 that are nearby the new well that's planned, so where they have new activity coming up, and then we'll do our evaluation of those 4 wells to basically set the stage for the new activity that the operator is intending. And that makes the project much faster, much cheaper, and more focused. And of course, if you're in these large fields, really the wells that are going to interfere or have an impact on your new well are the ones that are close by. If they're 10 kilometers away, it's not going to do much. So at least not quickly. So we have done projects in all phases. Okay. Certainly in say shallow offshore, we've done those kinds of projects. Usually there are issues that the operators want to address, and then this is a constant workflow, but to address, it doesn't matter what the issue is they want to address, the workflow addresses it.
Yeah, yeah.
I see a question in the chat box.
Yeah, in Colombia, just a quick
comment.
Oh,
yes, I'm sorry, go ahead.
In Colombia, for instance, as you know, as in many South American areas, most of the fields are in a mature phase.
Exactly.
So using RFG as a tool for production optimization sounds really interesting. Is that the first statement?
Yeah, but you're right that so many of these are old fields, and the old fields will have different issues than connectivity per se. They're generally, it's going to be associated with sweep efficiency, or it could be a sluggish aquifer. It could be viscous oil. We're not getting production that we expected. We're not sure why. Sometimes it's associated with viscous oil being where it's not supposed to be, that kind of thing. And we certainly get at those kinds of problems with this approach. And I'll just say we're flexible. So if somebody wanted to do this, but then the next question people say is, well, what if I don't have all that data? Like these, I'm showing studies with huge amounts of data, but we've actually done studies where there was literally no open hole wireline data that we could use from formation testing. And that was in Kurdistan, but we could still do it. We could still use the concepts that are present in this discipline to address their reservoirs, and the issues they had were which formations are going to produce, and do they have like incompatibility problems with the fluids. We could address those issues without having all this data. So it's really a concept more than a minimum data requirement. And once you start thinking, it's like in geology. You know, if you just said to the geologist, hey, you have to only treat the depositional setting, and that's it. Well, they're not going to be able to figure out even a structural trap, since all structural traps form in post-deposition. So what we're doing, I think, is opening the eyes of how to do this and how to frame it. And once you understand what Mother Nature does in these processes, that's when you can start to use that kind of knowledge in other reservoirs. So I would welcome an opportunity to look at Columbia reservoirs. We did one study in the Llanos Basin, but I would welcome that opportunity.
Excellent. Thank you so much, Oliver. Yeah, we have a question on the chat. Is from Batser. The question is, can you read the question, Oliver, or do you want?
Yeah.
To
So the question is, there are several service companies that provide measurements, formation testing. And what I'll say is this: we spent a lot of effort in Schlumberger when we realized the value of, and by the way, I'm grandfathered in, I say Schlumberger, you know, we're supposed to say SLB. Anyway, so we require accurate gradient data to do the thermodynamics. And I'll just say the tools, the optical tools, which we had built in Japan, our Japanese engineering center, and all the optics, those tools had to be extremely accurate with no tool-to-tool variation or minimized, and no variation in from environmental factors. And it had to be accurate. If it's not accurate, and there's plenty of not accurate data, then you can still collect a sample, but you cannot determine, for example, this offset. This offset was a huge issue to the operator because it meant that the seismic imaging could not be overinterpreted in terms of what's a pinch out. And we were correct. But if you can't measure with accuracy these kinds of small differences in the ODs, then you can't do the evaluation. So I'm going to say that of the RFG case studies, I personally probably have, I'm going to say 50 or 60 papers, and I have a whole pile of reservoirs that are unpublished because it's confidential data. I think we're the only people in the industry that have published an RFG study of this sort because of this data accuracy issue. Well, there's a know-how that goes into it, but if you don't have the data, you're sunk.
Excellent. We have another comment question from Micah.
Yes, I like this question. So if fluid analysis and modeling application that makes complex PVT are considered by reservoir simulation, what are the differences in results by considering this workflow? So this is an interesting question because the issue that we're often addressing, we always address here's what we don't do. We don't go to an asset team. I'm normally dealing with asset management, the lead manager of the reservoir, the asset manager. And we don't say, hey, we can address these 4 issues, pick one or two, and we'll address it in your reservoir. We don't do that. We go to the operator and we say, what is your biggest uncertainty in the subsurface associated with your reservoir? Or maybe the top 2, or maybe the top 3 uncertainties. And the answers that have come back are actually on page 9 in the front matter, IX in the front, the Roman numerals in the front matter, because we have heard all kinds of different reservoir concerns. Connectivity, so I have a chart, a table showing the 18 reservoirs that are in the book and various issues, and then the RFG processes in play. So the issue is always connectivity, but often it could be viscous oil, or it could be tar mat formation, or sluggish aquifer, or GOR gradients, or wax, or flow assurance. These are the issues that the operators tell us. The point I'm trying to make is that we are basically reducing the risk associated with the geologic model and the filling of that geologic model with the reservoir fluids prior to simulation. It's all about the geologic model and the fluid complexities in that model. Once the operator has an accurate understanding of the geologic model and the fluids that are embedded in that model, they know how to do simulation. So what we're really providing is not, gee, we can simulate your reservoir. We can do that. We have a lot of reservoir engineers, but many of the operators would prefer that they'll do the reservoir simulation. What we're really doing is reducing the risk in the reservoir description in the geologic model that they're going to then port to a dynamic model to simulate the reservoir and to develop their FDP. So that's really the primary focal point, is risk management in these reservoirs.
I have another question, Oliver. And how can this workflow can help, or how this workflow can be integrated in carbon capture?
Oh, that's a very interesting question. Well, there are a few ways. One thing I would note is Mother Nature has been adding CO2 to reservoirs since, forever. And so then you could say, well, can you use reservoirs that have been filled by that have had huge or substantial charges of CO2? I guess I'll go to my simulation slide. Can you use any of those reservoirs to help understand the evolution of what CO2 does in reservoirs? And the way I look at that is, I think so, because in CCS, of course, you're going to forward model everything. But if you have never done CCS for 50 years, which nobody has, then your forward modeling simulations could have errors that are not being properly accounted for. When Mother Nature has already added in some reservoirs 100% CO2, some reservoirs it's 80%. We have tons of case studies of all natures. Then you can model that in a geologic time frame and predict present day over long time spans, and then speed up the simulation. So we have done exactly that. So for example, when we charge the gas in this reservoir over 100,000 years, which is, we can change the duration of the gas charge in the simulation, there's no free gas that gets to the top of the reservoir unless the oil becomes saturated. But if we charge that same volume of gas in 100 years, a lot of free gas gets to the top of the reservoir because it's too fast. It overwhelms. You can't mix the oils the undersaturated oil, bring it around fast enough to get that huge volume of gas dissolved in the oil. So then we end up with a gas cap. So you can do some simulations. You can then history match what Mother Nature has done on the charge of CO2. And the other guidance you can get is when you have large volumes of CO2 going into reservoirs, like in the pre-salt, for example, or in the Songhong Basin offshore Vietnam, or Hainan Island, this basin south of that, as well as the Hong Song next to the west. Lots of CO2, and any reservoir near a plate boundary is going to get loaded with CO2. Same in West Africa. So you can use what Mother Nature has done to check, is your modeling working to predict those reservoirs, and then you change your durations of your charge. That's one way to use this into the CCS world. The other thing I'll just note, CCS also has diffusion mediated convection, and so that's an important process in geologic time. It may or may not be in the CCS timeframes, but that's something that could also be incorporated into the modeling, is the CCS mediated. The carbon, as you inject CO2, the CO2 diffuses into the liquid, creates a denser liquid than was originally there, and that'll convect. And I show an example of that in my book. So
excellent. Oh, that's great. Very, very interesting. I think it's almost 6 p.m. If there is if no additional questions, we can close the event. And if someone has any additional question or comment, please, you can send us a message, and we can pass the message to Oliver. Okay.
Indeed, I welcome any inquiries, or if you saw opportunity to try this out, or I'm always interested. I have never seen a reservoir I don't like. So if you have any possibilities, thank you so much for this opportunity. Greatly appreciate it.
Yeah, thank you so much. Back to you, Maria Florencia.
Thank you. Just a moment. Well, thank you all for being today connected. Bueno, gracias a todos por haberse conectado hoy. Déjenme compartir la última lámina. Simplemente invitarlos a que nos sigan nuevamente. No sé si están pudiendo, si se ve o no. ¿Me confirman, por favor?
Sí, se ve perfecto. Gracias.
Muchísimas gracias, Ulises. Bueno, agradezco entonces a todos por la participación de hoy, por el interés en participar y de estos webinars. También agradezco al señor Oliver Mullins por también participar del evento. Muy, muy interesante. Hay muchísimo por digerir acá, muchísimo material. La verdad que creo que todos hemos visto algo de esto en algún momento y hay mucho por profundizar. Los invito entonces, bueno, a que nos sigan en redes, a que nos escriban, a que se sumen, tanto al comité como también a las sesiones que vamos a ir compartiendo y realizando a lo largo del año. Y bueno, una vez muchas gracias a todos. No sé si quieren que saquemos una fotito antes de cerrar, una foto grupal, y damos ya por finalizada la sesión.